audience raised his hand and objected to the fact that I had never passed one of my qualifying exams. So it's sort of thing dogs do his whole life. But it's fun to think back on those days. When I was a graduate student, it was very exciting at Berkeley, lots of stuff going on. One of the things I tell graduate students who are feeling that they don't understand anything, everybody seems to know what a negative is, I sort of comfort them by saying, you think you had it bad? When I was a graduate student, we had, I had co-graduate students, Thurston, Yao, Rubenstein, and I never even get around to talking about what happened when the lecturer showed up. Mike Freedman was there as a lecturer the last year or two and seemed to know everything. And I was struggling to understand four manifolds, and he had the whole picture. So it was a great time, and it's fun to celebrate that now, I don't know, 40 years later, roughly. Okay, so this is joint work with Bob Gaunt and Abby Thompson. It's a combination of stuff from 3 manifolds and 4 manifolds. Probably if Bob were giving this talk, it would be quite a different talk. There'd be more emphasis on the sort of what will be the last part of the talk here. The 4 manifold side, I'll be talking more about the 3 manifold side. So let me start by talking about the motivation for the, So in 1987, Dave Jabbi proved a theorem which was in some ways the biggest vindication of the super-manifold approach to 3 manifolds. Solved a very old problem, one with ramifications in 4-manifold theory, which is why we have that connection now. He showed that if surgery on a knot inside of S3 gives S1 cross S2, then the knot has to be the unknot. If the knot is the unknot, then the complement is a solid torus, so it's possible to do surgery on that to give S1 cross S2 just by basically doubling the solid torus. What he actually proved was a little bit broader than this, but this is a good, well, this was in some sense the crucial question that people had. But it gives rise to a natural question. Suppose we think not just about a knot, but how about a link of several components inside of S3, and we know that surgery on the n components gives a connected sum of n copies of S1 cross S2. A natural question is what is the link L? You can get off to a roaring start, as people did when they thought about this. Just from using homology arguments, you can show that any pair of components is algebraically unlinked, and if you think about the surgery framing, they all have to be the 0 framing. Notice it's an important aspect of this. Whoa, how did I do that? I should stress algebraically unlinked here. We don't know that they're geometrically unlinked. It turns out that the link can be divided into 2 separate links, and you can work on them separately, so that's kind of the uninteresting case. But this is meant to be a schematic picture. That unfortunately is hard to draw for dimensions, so I've tried to divide it in two. So what you should see along the bottom here is, think of this as a copy of the 4-ball, to which you've added two handles. Here's one of them, V, I think it's green here. The chord is green. And another two-handle, U, which originally goes like this. Trying to draw this now with red. What you're seeing in motion here is that the red one is being passed over the green one to give a new two-handle whose core is this red curve. So that's what we mean by a two-handle slide. And without a lot of fuss, you can see that if you were just looking at what happens on the boundary of the 4-ball, namely on the S3, it looks like the band sum operation I described. There's another thing going on here that will eventually be moderately relevant. If you think about it, adding a two-handle in dimension 4, that's a D2 cross D2, so there's a dual picture in which you have a two-handle that's dual to the original one. So I tried to draw that here, again, having the dimension, so it looks like a one-handle. The dual to U is U prime, and dual to V is this sort of V prime. And if you keep track of this and look at what happens when you do the two-handle slide over of U over V, and look at what happens to the dual handles, somewhat counterintuitively, what happens is that V prime, the sort of co-core of the original V, is slid over U prime. So sliding U over V is dual to V prime sliding over U prime. Well, I'm not sure if that's a convincing picture, but really it looks just like that, only it's 2 dimensions higher. So you know the way math works. When you realize there's a counterexample to this easy conjecture or naive conjecture, you try and incorporate that counterexample into your next conjecture. So a natural fallback conjecture is sometimes called the generalized property R conjecture. If surgery on n components is connected to some of n S1 cross S2s, then perhaps after these handle slides, you can arrange so that L becomes the unlink. Then the original counterexample I gave you a couple slides back is no longer a counterexample because that's exactly how it's constructed. This generalized property R is unknown, even for n equal 2. So it's a nice sort of borderline problem involving 3 manifolds, 4 manifolds, and the number 2. I mean, what could be lower than that? Well, 1 could be lower, but that's already done. So it's kind of a natural thing to think about. And one way of thinking about it, since someone's been able to prove it, is, well, perhaps it's wrong. Perhaps there are counterexamples. So then the natural question is, if it's not true, what's the simplest counterexample we could find, or at least the simplest plausible counterexample? And since links are intrinsically perhaps less interesting than knots, you could even turn it into a knot theorem, a knot problem, and ask, what's the simplest knot that could show up as part of the two-component counterexample? It doesn't get to be more sort of elementary in terms of being able to phrase the question than this. I mean, n is 2, you're looking at just one component. What can you say about one component? Well, there is a theory behind that. People have thought about this. Notice that the potential counterexample must be sliced in some homocopy 4-ball. So here's a quick proof of that. What we want to do is now take the picture that I described in the previous slide and sort of turn it inside out. So we're going to start on the outside with S3, and instead of thinking of S3 bounding a 4-ball with the two handles attached on the outside, attach the two handles, here denoted red and blue, on the inside of S3. Now, if the result of surgery on that link is connected sum of 2 copies of S1 cross S2, then the result of attaching these two handles, thinking of this now as a 4-manifold, S3 cross I and a collar, and you attach the two handles, the result has boundary S1 cross S2. You can attach 3 handles to the S2 factors in S1 cross S2 and cap off everything except the 4 handle. So, and what you In particular, there may be algebraic obstructions to a link being sliced inside a homotopy 4 ball, and those will immediately rule out that link as a possibility for doing surgery and getting 2 copies of S1 cross S2. Now, you can say even a bit more if you ask about the complement of the link versus the complement of the slicing disk. So let me say just a quick word about that. So I'm going to call that the slice complement. You imagine removing the slice disks and asking about the construction of the complement of the slice disks. Notice that what you're doing, if you try and build up the complement, you're attaching, first of all, copies of B2 minus 0. Minus 0 is because you've removed the center of the 2 handle because you're interested in the complement of the knot. So you're instead of attaching a 2 handle, D2 cross D2, you're attaching D2 minus 0 cross D2 to D2 minus 0 cross S1 in the S3. And if you think about what that means, you really just attach some 2 and 3 handles, and then in the construction I just described, you then add some more 3 handles and a 4 handle. So notice only 2, 3, and 4 handles are attached. This is very reminiscent of something that you've seen before. If you look at a ribbon disk for a link, well, there are many ways of describing a ribbon disk. And one way is to think of it as a slice disk in which, if you look at the radial function, there are only minima and bands. There are no maxima. And if you think through what that means for a handle value description of the complement, it is similar in the sense that only 2, 3, and 4 handles are attached. And one consequence of this observation is that if you think of about the fundamental groups, pi 1 of the link complement goes onto pi 1 of the disk complement because all that's been attached is 2, 3, and 4 handles. There's no nothing has been added to the fundamental group. So, well, let me just make up a term here, and I don't think I'll use it again, but it's the comparison here between what we can say about the fundamental groups of the link versus the link complement versus the disk complement might encourage one to think of this as being sort of topologically riveted. It has this property, the slice disk has the property that pi 1 is onto. Okay. Well, let's now think about the general question of in what circumstance can you actually prove the generalized property R conjecture, even for 2 component links. Well, the first theorem I know in this direction was due to Alan Reed, and I don't know that he ever published it. The reason I know about it is I gave a talk on this sort of problem in Texas, and somebody asked me, what's the simplest example you don't know about? And I said, well, how about, since property R was originally proven for tunnel number 1 knots, how about tunnel number 1 links? If you have a link of 2 components and you know that adding a single arc makes the complement a handle body, can you do it in that case? If you take that as a possibility. And so I threw that out as one where we didn't know the answer, and 3 hours later, Alan Reed was in my office showing me that it was true. So that's pretty nice. And the proof is fairly direct, though it's not one, I mean, it surprised me. I would never have thought of this. So here's a very quick argument. Free groups are obvious. So we just think about the fundamental group. So if we have a tunnel number 1 link, so that means it's a link with the property that adding a single arc makes the complement a handle body. In other words, has free fundamental group, rank 2. You can take here on the left there, S3 minus L union the tunnel is a free group, Z star Z. Then there's an anamorphism onto pi 1 of S3 minus L just by forgetting about the tunnel, filling it back in. That adds a 2 handle, and therefore that's an anamorphism. And the assumption is that by doing surgery, which adds a little bit more in the way of relations, you get connected some with 2 copies of S1 cross S2, which also has fundamental group Z star Z. So we have this apomorphism it's a very nice result, but somehow a little bit unsatisfying. Okay, so let's go back to the program I mentioned earlier and ask what's the simplest knot that could be part of a counterexample. And of course, if you're going to ask that question, one relevant question is, how about the unknot? Maybe the unknot could be part of a counterexample. And the answer is no. And a pleasant feature of the answer is that, first of all, it requires deep three-manifold theory to show this. And secondly, handle slides are visibly important for the argument. Okay, so let me say it as a theorem. If U is the unknot and surgery on the unknot union another component gives connectus on the two copies of S1 cross S2. Then after some handle slides of V over U, handle slides of U over V are not needed in this argument, then L becomes the unknot. Okay, so the idea here is because we are given very concrete information about U, we may as well sort of go halfway into the argument and think about what happens after we do surgery, zero-frame surgery on U by itself. Well, since U is the unknot, we know what surgery on U will give, namely S1 cross S2. I tried to indicate that. This picture is a little bit hard to decipher, maybe. It looks like, it's supposed to look like, anyway, S2 cross I, but I'm really thinking about S2 cross S1 by identifying the outside S2 with the inside S2, which of course is difficult to do in a two-dimensional representation in 3 space or whatever. Anyway, so you have the inside two-sphere identified with the outside. U, after surgery, becomes a knot inside of S1 cross S2, represented by U prime. That's the vertical blue bar. And in there somewhere is this other component V that so far we haven't used at all. So that's the picture that we have now. And what we know is, what we further know is that surgery on V will give us S1 cross S2 plus S1 cross S2. Now, it turns out that fits in very well with some earlier work of Generalized, which I think actually precedes a little bit property R. If we think about what V, the property V has, it has the property that if you just fill it in trivially, we have S1 cross S2. On the other hand, if you do zero-frame surgery on it, you get S1 cross S2 plus S1 cross S2. So there's sort of 2 ways of filling in V to get reducible manifolds. Well, Dave Gabbai, as part of his program in the 80s, showed that can only happen under very special circumstances. And the important point here is that V would actually lie inside a free ball inside of the original S1 cross S2. So instead of having a mess, which is the picture I had before, V being a mess, that immediately tells us that V is pretty nice in S1 cross S2. But it might still be hung up with U prime. There's no comment about how it relates to U prime. So one of the things we might have to do in moving V to lie inside a ball is to pass it over U prime, pass it through U prime. Now, if you think about the original picture, U prime is gotten from U by doing zero-frame surgery. So crossing the meridian of U prime, which is what you'll need to do to get V all by itself, is equivalent in the original picture to sliding V over U. So those are the handle slides that we've been looking for. And sure enough, it happens here sort of spontaneously. And once we get it then inside wall, it follows from the original one component case done by Gabbai that the original U and V are the unknown. So what this implies is that, well, as I said in the original theorem, that sliding V possibly multiple times over U eventually ensures that U together with V is the unknown. Yeah?
It's unintentional for that illustration to merge forward was the whole.
Here? Yeah, that's true. That's true. Yeah. It is unintentional. surgery on U first, we get a fiber manifold, and contained inside of it is the original component B, which is unaffected by the surgery, and then the dual knot to U, now called U prime. And what we know is that surgery on the component B in M gives connected some two copies of S1 cross S2. So we've replaced the previous argument, the previous situation, which relied on Gabai's theorem about two surgeries, with a similar situation. We're given a surgery, except instead of having S1 cross S2, all we have is a fiber 3 manifold. So it's a little bit of a different context, but it turns out that there's at least something that can be said. Again, this is all using sutured manifold theory, an older theorem due to myself and Andy Thompson, shows that if surgery on a knot inside a fiber 3 manifold gives a reducible manifold, and this one does because it gives connected sum of two copies of S1 cross S2, then there are a number of possible outcomes, 3 different outcomes, but only one is viable for a situation in which we're going to end up with connected sum of two copies of S1 cross S2, namely V lies in the fiber. So what we're allowed to conclude from this is that V lies in the fiber, but again, that's in the 3 manifold, and moving it into the fiber may involve sliding or passing V through U prime, in other words, sliding V over U. So after possibly sliding V over U, we end up with F lying inside a fiber. Well, what good is that? Now it's useful to think about what it means to do zero frame surgery on V lying in a fiber. It turns out the framing is the fiber framing. And so if we think about surgery on that, here's one way of thinking about it that will be useful. So what do we do when we do surgery? We remove a neighborhood of V, S1 cross V2, and one way to think about that is to imagine slicing this 3 manifold open along the fiber that contains V. And if you did that, well, you would have a fiber cross I, and you would have also scooped out just something from that fiber. Namely, thickening up V just kind of scoops out something from the 3 manifold. So there's like a little ditch dug both below and above at that fiber. That's what happens when you remove a neighborhood of V. When you attach the 2 handle, you can imagine, when you fill in the solid torus S1 cross D2, you can think of S1 cross D2 as 2 copies of I cross D2 glued together along their boundaries. And if you put one on each, one below and one above, it's like attaching 2 handles. So what you've done is you sort of dug a ditch and then attached 2 handles where that ditch was. Well, if that's getting confusing, this picture on the left is meant to be a kind of schematic picture of what happens. You divide the 3 manifold along the fiber and then attach these 2 handles, and then you glue them together somehow, just as you glued the top fiber to the bottom fiber. Well, there's a name for this. If you take a 3 manifold, surface cross I, and you attach a 2 handle to it in a non-trivial way, that's called a compression body. And there's a whole theory about what happens when you glue these things together. That is the theory of T-guard splittings. And so this is quite relevant to, or T-guard theory is quite relevant to the problem that comes up. And I'll mention something about that in a minute. But let's complete the argument here. Once you add the 2 handles, what was previously the surface F becomes the surface F prime with lower genus, corresponding sort of dual to the original non-V is the new core V prime, which we can think of as kind of a circle around the original tunnel that we dug. It consists of an arc below and an arc above along the ditches that I mentioned. And so what we have now is a copy of two copies of, well, we have a picture of connected sum of two copies of S1 cross S2, that's the hypothesis, and these two fairly well-defined components sitting in there, U prime and V prime. Well, just from this picture, and the fact that the blue only goes through F prime at a single point means that we can now slide V prime over U prime twice and get it away from F prime. So after doing a couple handle slides of, or band sums, maybe is a better term, of V prime over U prime, you get U prime intersecting F prime and V prime disjoint from it. So another way of saying this, two handle slides of V prime over U prime makes V prime disjoint from F prime. Well, as we saw in one of the original pictures, the handle slides of V prime over U prime corresponds to handle slides in the original of U over V. So now we're doing handle slides of U over V, which we've never done before, and that makes U have fiber F prime, which is a lower genus than F. Well, in an ideal universe, you could somehow iterate this process and end up proving it, but there doesn't seem to be an easy way to iterate this. But maybe I'll remember to say something about that issue a little bit later. Well, okay, so now we have an immediate corollary that if you think, since we know the unknot is not part of the counterexample, and we've just shown that if you have a fiber knot as part of the counterexample, you get a counterexample with lower genus. Well, that rules out genus 1. So you think about all genus 1 fiber knots, and there are only two, trefoil and figure 8 knots, and so one corollary was that these do not appear in any counterexample. But before you can get excited about that, you realize you knew that all along, because I showed that counterexamples, or just having surgery giving S1 connected sum of S1 cross S2 ensures that they're sliced in a Homotopy four-ball, and for simple algebraic reasons, we know that neither of these is sliced in a Homotopy four-ball. So there's very little advance there. Okay, so, but since thinking about genus 1 doesn't work, we turn to razor blade manufacturers and let's ask what number comes after 1, and the answer is 2. So we might start thinking about genus 2 fiber knots, and we think of a counterexample there. And because it didn't work well, the genus 1 case wasn't so enlightening, we have to start out from the outset to make sure that we're looking at a fiber genus 2 knot, which is sliced in a homotopy, in some homotopy 4 sphere. And immediately, sort of the simplest example that might come to mind is a square knot. So I'll let Q now. So Q is going to play sort of the role of U in the previous argument, but I want it to be the specific example of the square knot, which we actually saw before in the one counterexample I gave to the naive conjecture. It's the trefoil plus its mirror image. So let's see what we can say about that. Well, there are plenty of links. You can make plenty of links that surge to S1 cross, two copies of S1 cross S2 and involve the square knot. Just by going back to the original example I gave, consisting of the unknot union, the square knot, but this time instead of simplifying the square knot by sliding the blue over the red, we could complicate the unknot by sliding the red knot over the blue. And then you get, well, it's on some sort of schematic picture of how complicated things could get if you take a complicated band. And in any case, you could get lots of examples of complicated links containing the square knot so that the surgery gives connected sum of two copies of S1 cross S2. But we also know that none of these examples could possibly be counterexamples because you can always undo those operations and end up with an example that we've shown is not a counterexample to the generalized property R conjecture. So that's a first observation. The next question is, well, suppose you ask more generally, what knots can we add to the simple and the monodromy so well defined, and because we know that this other thing after possible slides, the other component D after possible slides over Q, will end up in a fiber, it actually turns out to be not so hard to give a description of all possible links up to that sliding over Q that have the property that surgery gives connected sum of two copies of S1 cross S2. I won't describe that. It's a little bit complicated to describe, but in some sense it's also very straightforward. So I do want to mention that P-guard theory comes in trying to understand this. Namely, one of the features you discover when you use the fact that the P-guard splitting I sort of briefly mentioned earlier has to be a weakly reducible P-guard splitting, is that the monodromy involved, in the picture I showed you, if you think about the monodromy involved in the gluing of F, the two handles that are attached, I'm being very schematic here, have to actually be on disjoint circles. And that's enough, so that information all comes from P-guard theory, and it's enough to allow you to rule out lots and lots of possibilities for such feeding, and eventually focus on a collection that can be easily described. If you're curious how this picture is reconciled with the previous picture that looked sort of P-guard-y, the thing to realize is it's schematic in that the two handles that are being attached actually should be kind of thought of running all the way through these compression bodies and being capped off to give F prime. So it's a little bit schematic here. Anyway, suffice it to say that by using P-guard theory and actually do slides and make the thing the standard force sphere. So we know that it is a standard force sphere, but if we weren't allowed to stabilize in the way I've described, we wouldn't know that. Or at least it would be very difficult to show that because it's believed that you can't make this Andrews criticism. So, let me say one thing about this presentation, which probably means nothing to many of you and is very simple for others. The red and the blue dot, those two handles aren't really two handles. They're gotten by sort of scooping out two handles from a four ball. So in particular, they represent the fact that the other things on which you're doing surgery are, I think they're red and black there, are actually two handles that are being attached to the boundary. What you get by scooping out these two handles, namely, the boundary would be connected some of two copies of S1 cross S2. Well, one question then is, it's easy, or at least fairly straightforward to see that the result has boundary S3. So one can then ask the question, how do you turn this upside down? So instead of thinking about starting with S1 cross S2 plus S1 cross S2, which is the picture Bob had drawn, one of the things we want to understand is what happens if you look at a dually starting with S3 and attaching two handles. And there's a process called turning it upside down, I think, which Bob formally describes in his book how it works, and it only makes the picture more complicated. And in particular, the previous picture now becomes the picture on the left with brackets around various numbers, etc. So, but the upshot is that the picture on the left is meant to code a way of attaching two handles to S3 to get two copies of S1 cross S2, and moreover, they are known to be, it's known via this Andrews-Curtis argument, to be very hard to try and make it trivial by doing two-handle slides. So immediately you start seeing that it's very relevant to what we've been thinking about. And sure enough, I mean, this is in the middle of his lecture, Bob said, well, let's do a simple example. And he did a simple example, and there was a square knot. And of course, that would fit in very well with what I've been wondering about. So here we were, an example of a length of two components, one of which is the square knot. The other is, I'll call it BN here. It's connected some of two torus knots, and it's interleaved with a square knot in the way I've shown here. And surgery on that gives S1 cross S2 plus S1 cross S2. But if one could show that it actually was not a counterexample of generalized property R conjecture, in other words, if you could show that you could slide things around so eventually it became the unlink, then you would have been able to show that that presentation of the trivial group was Andrews-Curtisable. So the point is, well, we don't know what the answer is, but either you found a counterexample to generalized property R with just two components and the world's simplest possible counterexample, not contained in the world's simplest possible knot appearing in the counterexample, namely the square knot appearing in it, or you've shown some way that this presentation is Andrews-Curtisable. So that's kind of exciting. And we might hope then that it's actually a counterexample of generalized property R. Now, there's another strand of this argument that I should mention. The canceling 2 and 3 handle pair, which Bob had used to show that the Homotopy 4 ball was actually the 4 ball. You can sort of follow that strand and ask, well, what's the equivalent question here? And the equivalent question here would Anyway, so there's this whole branch which I think I'm not going to go into, but it's kind of a provocative direction, I think. I should mention that one feature of this link is that it's, for reasons I've kind of described, is, although it's not obviously ribbon, it is topologically ribbon in the sense I described before, namely there is a slicing of it for which the fundamental group looks right. If you don't like slice lengths, you can turn it into a slice knot by doing a bandsum on it. And so here's an example of something that we know to be slice, but there's no, well, it's certainly not apparently ribbon. And one of the features of the slice versus ribbon is that it's somewhat difficult to come up with examples that that are built in a way that they're not visibly ribbon, I'm told. So this is one thing you can think about, trying to figure out whether this is ribbon or not. Let me conclude. I think it's roughly time to conclude here. Okay. Well, let me talk a little bit then about the questions that can arise. So I mentioned that in trying to prove, well, hopefully trying to prove that the square knot was not part of the counterexample. Now it seems that that was a faulty direction to be going. But one of the things we discovered is that there was a way of classifying all possible additional components one can add to Q so that you get connected sum of two copies of S1 cross S2. And so here's an example. And the question is, how does it fit into the classification scheme? Well, it should be an easy question to answer until you remember that the classification scheme meant up to sliding over Q. In other words, you have this example here, and all you know is that if you slide over Q a number of times, that it should end up lying in a fiber. When you look at the actual example, it doesn't look like it lies in a fiber. In fact, it seems very hard to imagine how it lies in a fiber. And just to sort of taunt you, there is a very simple example of connected sum of torus knot and its mirror image that does lie in a fiber, but it seems to be the wrong example. It doesn't seem to be the example I just described. So one question is, how does this counterexample fit into that classification scheme? And if we knew how it fit in, that would be quite an interesting example, I think. washes out the whole problem. That would be,
Really, because that seems to correspond to being able to have three handles.
right, right. I mean, I literally mean that, but maybe there's some elementary way of seeing it, but we weren't able to see what to do with that. But that is the natural weekend thing corresponding to the three manifold theory, namely adding both the hop and the unlink of our components and then doing a slide and slides